So last time we talked about kinetic energy. Today we're going to talk about different types of energy and what it means for energy to be conserved. So kinetic energy, we said, was the energy of motion. And we wrote down this nice convenient formula, which is 1/2 the mass times the velocity squared for the kinetic energy. Now it turns out that's not the only way an object can move. Right? It doesn't just have to be moving in a straight line. It could be rotating. So suppose we have some wheel. I happen to have one right here. Well, if my wheel is spinning around, it also has some energy to it as well, except it's not going anywhere, so I can't really give it a velocity. Instead, I would have to give it talk about its angular velocity, and we'd have to talk about a different type of energy. We would call this rotational kinetic energy. Some of you have the way angular velocity. Rotational kinetic energy. So that's another type of energy that we could have. And in fact, these two are the only two types of kinetic energy we're going to discuss. In fact, they're the only two types of kinetic energy we have. There's just moving in a straight line and rotation. Now, I could have an object that has both of these. Maybe it's a wheel that's rolling down the street. Therefore, it would have some velocity. It would have some angular velocity. And we could talk about both kinetic energy and rotational kinetic energy. But these are the two types of kinetic energies that we have. Next, we're going to talk about a bunch of different potential types of energy that we have. Next, we're going to talk about potential energy. Now, potential energy is called potential energy because it has the potential to turn into kinetic energy. So, for example, here I have just an eraser. Right now, this eraser has some potential energy. The reason it has potential energy is because I am lifting it off the ground. And if I have lifted it off the ground, as soon as I let it go, it can get kinetic energy. So that tells us there's got to be some potential energy stored in my eraser. And in this case, that type of potential energy, since it's gravity that's going to be doing the work on the object, is gravitational potential energy. So another example of this is one of my favorite YouTube videos. Again, if you have a cat on a table, and then maybe here you have a flat screen TV, the cat likes to do experiments with gravitational potential energy because here your flat screen has some potential energy, which when your cat knocks it over is going to get converted to kinetic energy. Similarly over here, let's say I have a spring. So I have a spring and I take a ball and I press the ball down on the spring. Well, once the spring is compressed, as soon as I let that ball go, it's going to want to come shooting up. So we could talk about the potential energy stored in a spring. Over here, I have drawn what I hope is a glucose molecule, although I could be wrong on that. But we could talk about chemical energy. So there's a lot of ways that I can store energy in different chemicals. The common examples, at least biologically, are sugar, fat, and protein. Okay, so you eat sugar, fat, and protein. That gets turned into ATP. You use that as a chemical with which your muscles can do work. If you're talking about a car, the chemical energy that you use there is just gasoline. Okay, so it could be gasoline, could be diesel. If you're in a rocket, it could be rocket fuel. Lots of different types of chemical energy. Other types of energy we have, other types of potential energy. Suppose I have two electrically charged objects. They're both positively charged. What do two positive charges do to each other? Well, they're going to push each other away. So if I just brought them close together, I would have to do work to push them close together. If I let them go, they're going to repel each other apart. Similarly, if I brought a positive and a negative charge together, as soon as I let them go, again, they're going to start to move. They're going to gain kinetic energy. if that's the case, there has to be some potential energy that gets converted to that kinetic energy. We could talk about magnetic energy. So here, I have two magnets. Right now, I've got the south pole of one magnet connected to the north pole of the other, and they stick together. However, if I flip those two poles so that they point, so that I have a north pole pointing to a north pole, what we can see is there's some potential energy there. As soon as I let them go, they're going to have, they're going to get kinetic energy. That potential energy gets converted to kinetic energy. Because by magnets, we know that north poles repel north poles, south poles repel south poles, and north poles are attracted to south poles. So in this case, I would get some kinetic energy because they're going to repel each other apart. Similarly, we're going to talk about this one later in the course. We could have thermal energy. So when you heat an object up, in fact, you don't even need to heat it up. Any object that is at any temperature that's not 0 Kelvin has some thermal energy associated with it. Okay, so thermal energy, you can think of it as the random motions of the molecule inside the object. So the sun is very, very hot, which means the particles inside the sun are whizzing around very, very quickly. And if they do that enough, eventually that object will start to glow. So it gives off thermal energy, two types of energy here. One is the thermal energy going around in the sun. We also have radiant energy because there's energy in the light that comes down and that we absorb on our bodies if we're not wearing any sort of sunscreen. Or we could have some sort of solar panel that we can use to convert that energy into useful energy to power our laptops or smartphones or whatever it happens to be. So why are all these different types of energies important? Well, they're important because we have this rule that says that energy is conserved. So that we can go back and forth between one form and another, but we always have to keep the same amount of energy in total. So what exactly does it mean that energy is conserved? How can we use that to our advantage? How can we understand that physically? So what does it mean for energy to be conserved? Well, suppose I have some initial total amount of energy. I'm going to call that E sub I. So that could be a bunch of different types of energy. It could be my kinetic energy. It could be that we have some rotational kinetic energy. It could be that we have some spring potential energy. We'll call that U spring. So usually, potential energy gets the symbol U. And then I'll just use some subscript to determine what type of energy it is. So we could also have some chemical energy, maybe some electrical energy. We could have a bunch of different types of energy. I've only given you a few different forms of energy, but we could have many different types of energy. However, no matter what type of energy we have a very simple statement when it comes to total energy is conserved. All we would say is that the initial energy has got to be equal to the final energy. This is a physical law. All energy is conserved. So if I look at the total energy initially, I've got to get the same thing when I look at the system at a later time. I'm always going to have the same amount of energy in total. I think the best way to illustrate the principle of conservation of energy is to do an example. Before doing that, I want to give you an equation for one type of potential energy, specifically gravitational potential energy. So let's say we have a ball. I take the ball and I raise it to some height h. Well, it turns out the amount of gravitational potential energy is pretty simple. It is just given by this formula. It's the mass times gravity times the height that I have raised it to. Now you might ask, well, why does it have that form? And the reason it has that form is pretty simple. So suppose I start with the ball on the ground. Well, It doesn't have any potential energy if it's on the ground, right? I can't drop it if it's on the ground. So it can't gain any kinetic energy by dropping it. But if I were to raise the ball by a certain height, I would have to do some work on it. The amount of work that I do is, again, just the force times the distance. Parallel force, I should say, because it's in the direction that I'm pulling it. So say I pulled it straight up. Well, I would need to pull with a force that directly cancels out the force of gravity on it, which means the force that I'd be pulling with is m times g, because that's the force that gravity pulls with. And I will have pulled it a distance h. Therefore, the amount of work that I do is mgh. We know by the work energy theorem that if I do a certain amount of work on it, I change its energy by that amount. So by pulling with a force equal to the force of gravity and lifting it up a height h, I've done work mgh. Therefore, my energy is changed by mgh, and I can call that my potential energy, my gravitational potential energy. So you'll want to write this down. This is the formula for the gravitational potential energy of an object of mass m that's been raised to a height h on the surface of the Earth. Now that we have our gravitational potential energy formula, let's do an example. I'm going to go back to my kitty example that I had before of a cat knocking over a flat screen TV. So suppose you have a flat screen TV of mass m, and it is located on a table that has a height h. I want to know what's the velocity that flat screen is going to hit the ground. And I want you to find it using either kinematics, well, first using kinematics, and then using the conservation of energy. So how do I find it using kinematics? How do I find it using conservation of energy? Well, we can do it in both ways. Let's see how that's going to work. Erase this. So first, let's find how fast it hits the ground using kinematics. Well, I can go and look at my kinematic equations. And one of my kinematic equations is v final squared minus v initial squared equals 2a times delta x. Now, for the purposes of this problem, let's try. Let's say that our mass of our flat screen is 10 kilograms, and the height is 1 meter off the ground. All right, well, I look here. Initially, my flat screen has 0 velocity, so that's going to be 0. I want to find my final velocity. I know the acceleration, once it gets knocked off the table, is just due to gravity. That's going to be 9.8 meters per second squared. And it's going to travel a distance equal to the height, which is just 1 meter. So, plugging in here, we could say that v final is going to be 2. This was equal to g, so we'll say 2 times g times the height, and then I've got to take the square root to solve for v final. Okay, so this is my answer. And if you plug in numbers here, so you take the square root of 2 times 9.8 meters per second squared, always put your units in your calculation so you can see what cancels, times 1.0 meters, you should get, assuming I did my math correctly, you should get about 4.4 meters per second. One note on this calculation. I did define the down direction as positive, just to make my life easy. Suppose you didn't do that. Suppose you wanted to keep up as positive. Well, you could do that too. But that would mean that g is negative 9.8 meters per second squared. It would also mean that the distance you travel is negative 1 meter, so the two negative signs would cancel anyway and give you a positive number here, which it has to be because you can only take a square root of a positive number. So here, we've got that our flat screen TV hits the ground at 4.4 meters per second. How fast is it going to travel? How fast is it going to hit the ground if I do the same calculation using conservation of energy? Let's see. Well, here's what I know about conservation of energy. I know that my initial energy has got to equal my final energy. What is my initial energy? Well, initially, if the cat's just dropping the flat screen off, it doesn't have any kinetic energy. It's not going down yet. It's just been pushed slightly to the side. So we would say we could have had kinetic and potential energy, but initially we had no kinetic energy. It was all just gravitational potential energy. Finally, the final energy, again, we could have kinetic or gravitational potential energy. But in the final picture, the flat screen just about to hit the ground. So if it's just about to hit the ground, that would mean its height is 0. So it doesn't have any more potential energy. It's not going to gain any more kinetic energy right before it hits the ground. Okay, so let's see what that would mean. Well, UG, gravitational potential energy, would be the mass times g times the height. And that would have to equal the kinetic energy right before it hit the ground. So this would be the final kinetic energy. In fact, this would be the final gravitational potential energy. This would be the initial gravitational. This would be the initial kinetic energy. So we have mgh equals final kinetic energy, 1/2 m v final squared. So I look here, and I say, oh, my m's are going to cancel out. I can move my 2 over to the other side, and I will get v final on this side equals 2gh, and then I have to take the square root. That's the same thing we got when we used kinematics. So I can use conservation of energy, I can use kinematics, but I should always get the same answer. Either way, I should get the same answer. And in fact, energy is going to be even easier to work with, because I can use energy in more complex situations than I can with kinematics. So energy gives us a very powerful tool with which to do calculations.